everyone, I'm back. This is Teacher Joanne from Math Room. Once again, we will be having another lesson in general mathematics, and the topic in this video is all about rational functions. So here are our learning objectives. First, you should be able to find the domain and range of a rational function, and second, determine the intercepts, zeros, and asymptotes of rational functions. So at the end of this lesson, you should be able to answer the essential question, what are the different properties of rational functions and how to find each one? First, take a look at the following graphs. What can you say about these graphs? All of these graphs are examples of rational functions, and you are going to learn the properties of this function. Let us first define rational function. The function here f of x is equal to x squared minus 4x minus 5 all over x minus 4 is an example of a rational function because it is a function of the form f of x is equal to p of x over q of x, where p of x and q of x are polynomials and q of x is not equal to 0. Rational function expresses the relationship between two variables such as x and y. Now, let us have the properties of rational function. So we have the domain, range, the asymptotes, vertical, horizontal, and oblique, and intercepts we have x-intercept and y-intercept. Now, let us discuss each property. Let us use f of x equals 1 over x plus 2 to discuss each property. And we can see on the right side the graph of this function. Domain is a set of real numbers excluding the value that will make q of x equal 0. So here we have to look at the denominator of the given function. So in our given function, we have f of x is equal to 1 over x plus 2. So again, to find the domain, we have to look at the denominator and exclude the value that will make the denominator 0. So since we have x plus 2 in the denominator, all we need is to equate this to 0 and solve for the value of x. So here, x is equal to negative 2. So with this value, we can now see that the domain of the function is a set of x such that x is not equal to negative 2. Meaning to say, we can use any real number to x except negative 2 because it will make the denominator 0. And once again, if the denominator is 0, the entire function will become undefined. And looking at our graph, it is very obvious that the two graphs of this function do not pass through negative 2 on x. So negative 2 is the value that is excluded in our domain. Let us now discuss how to find the range. So for the range, we have to base it from HA or the horizontal asymptote in most cases. Or we need to sketch the graph of the function to find the range if there is no horizontal asymptote. Later, we will be discussing the horizontal asymptote. So for now, let us take a look at the graph of the function so that we will be able to get to know the range of this function. So as we can see here in this graph, this portion of the graph goes upward continuously, meaning all positive values are being covered by the function. While here, as we can see, the graph is moving continuously downward, and with that, all negative values are part of the graph as well. But as we can see here, the two graphs are not passing through 0. Therefore, 0 is the value that is excluded in the range. So the range of this function gives us set of y such that y is not equal to 0. And later, I will show you how to find the range using the horizontal asymptote. First, how do we define asymptote? When we say asymptote, it is a line that is being approached but never touched by the graph of the function. In this case, looking at these two graphs of our given function, these two are not approaching the vertical line that is here on point negative 2. Okay? And this one is what we call the vertical asymptote. And then the other asymptote based on this graph is this line, which is the horizontal line. The y equals 0 Therefore, we call this as the horizontal asymptote. Now, let us discuss the different asymptotes. So again, we have the vertical asymptote. So vertical asymptote is represented by x equals a because x is constant in that given vertical line. And to find the vertical asymptote, first, reduce the rational function if it is possible. Second, find the values of a that makes the denominator 0. So in our given example, f of x is equal to 1 over x plus 2. To find the vertical asymptote, all we have to do is to equate the denominator to 0. So x equals -2. So this is the vertical asymptote of the given function wherein the graph of the rational function does not pass through x equals -2. Next, we have the horizontal asymptote. Horizontal asymptote is represented by y equals b because the value of y is constant in the horizontal asymptote. And a graph of a rational function can only have at most one horizontal asymptote, meaning a rational function can have 0 horizontal asymptote or 1 horizontal asymptote. And to find the horizontal asymptote, let n be the degree of the numerator and m be the degree of the denominator. So if n is less than m, meaning the degree of the denominator is greater than the numerator, the horizontal asymptote is automatically y equals 0. But when n is equal to m, the horizontal asymptote is equal to y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. If n is greater than m, there is no horizontal asymptote. In our given function 1 over x plus 2, let us identify the degrees of the numerator and denominator. For the numerator, since it's a constant function, the degree of n is 0. And for the denominator, it is a linear function, so the degree of m is 1. As we can see here, the value of n is less than m. Okay, since 1 is greater than 0. So in this case, it follows the first. So the horizontal asymptote of this function is y equals 0. The next kind of asymptote is the oblique asymptote. It is an asymptote that is neither vertical nor horizontal, meaning it is slanted. This exists when the degree of n is greater than m, meaning there is no horizontal asymptote. And the oblique asymptote is represented by y equals mx plus b. To find the oblique asymptote, we need to divide the numerator, p of x, and the denominator, q of x. And the quotient is the oblique asymptote. In our given function, f of x equals 1 over x plus 2, since we have horizontal asymptote based in our previous discussion, here, the oblique asymptote is none, meaning there is no oblique asymptote. Next, let us discuss how to find the intercepts. When we say intercepts, these are points where the graph of a function intersect with the x-axis and the y-axis of the Cartesian coordinate plane. So here, what you have to do is to look at the x and y, and if the graphs intersect at the x and y, then we have x and y intercepts. In this case, looking at the graph, these two graphs did not touch the x-axis, so it is none, no x-intercept. As for the y-axis, this graph passed through the y-axis at this point, therefore there is a y-intercept which is y equals 1/2. Now, let us discuss the x and y. How are we going to find them if we don't have a graph? First, x-intercept. It is a value of x when y equals 0. It is a point on the x-axis with coordinates x, 0, where the function f of x crosses. The other term for x-intercept is 0. Now, in our given example, f of x is equal to 1 over x plus 2. Let us change f of x to y. Then, let us do this procedure. Let y be 0. We are now solving for x, so to remove this denominator, we have to multiply it to both sides. So we have x plus 2 times 0 is 0. equals 1. Since 0 is not equal to 1, the x-intercept of this function is really none. And it was very obvious in our graph in the previous slide. As for the y-intercept, it is a value of y when x is 0. It is a point on the y-axis with coordinates 0, y, where the function f of x crosses. Based in our graph, we have the y-intercept equal to 1/2, so let us show it algebraically. So if we have f of x is equal to 1 over x plus 2, change the f of x to y, then let x be 0. So it is really true that y equals 1/2. So this is our y-intercept. To summarize all the properties for this given function f of x is equal to 1 over x plus 2, we have the domain, which is x not equal to -2. To find this, once again, we have to look at the denominator and equate this to 0. As for the range, we have y is not equal to 0. Based in our graph, the graphs did not pass through 0 in the y-axis, therefore y is not 0. For the vertical asymptote, x equals -2 by equating the denominator to 0. For the horizontal asymptote, since the degree of the denominator is greater than the numerator, we are following the first case, which states there that if n is less than m, the horizontal asymptote is y equals 0. And as for the OA, since we have horizontal asymptote, there is no oblique asymptote. And as for the x-intercept, doing it using the graph, the two graphs did not pass through any point on the x-axis, therefore it is none. And doing it algebraically, let y be 0. As for the y-intercept, looking at the graphs, this graph passed through the y-intercept at this point, which is 1/2. And doing it algebraically, let x be 0. To show you the summary of the properties, here are the following steps that you need to take note. Now, let us find the properties based on the graph. First, domain. As we can see here on the x-axis, the two graphs are not touching 4. Okay, so all of the points going to the left, all of the points going to the right are being covered by the graph except 4. Therefore, the domain here is x not equal to 4. As for the range, as we can see on this graph, on the y-axis, this one is going downward continuously, this one going upward continuously. So all positive and negative values are part of the y except for 0. Therefore, the range is y not equal to 0. As for the vertical asymptote, since the two graphs did not pass through 4 on the x-axis, there is a vertical asymptote that is present here. Therefore, the vertical asymptote is given by x equals 4. Next, for our horizontal asymptote, looking at these two graphs, both of them are not passing through y equals 0, this horizontal line. Therefore, HA is equivalent to y equals 0. And since we have HA, therefore, there is no oblique asymptote. As for the x-intercept, it is the point on the x-axis that the graphs intersected. In this case, there is none. Therefore, we have x-intercept none. As for the y-intercept, this graph passed through the y-axis at this point, and this one is equivalent to y equals -1/4. Next example, we have f of x is equal to 3x plus 1 over x plus 2. For the domain, let us equate the denominator x plus 2 to 0, and therefore we'll be able to get a value that is -2. And for the domain now, it is set of x such that x is not equal to -2. For the range of this function, we can base it on the HA. So here, as we can see, the degree of the numerator is the same with the degree of the denominator. So the HA is the quotient of the coefficient 3 over the coefficient 1. 3 over 1 is 3. Therefore, the range here is not equal to 3. For the vertical asymptote, we we have to look at the denominator once again, equate it to 0, we will have negative 2. You have to take note that whatever is the value that is excluded in the domain, that is the equation of the line for your vertical asymptote. Same is true with the range. Whatever the value here, it is also the value in your HA. So we have y equals 3. For the x-intercept, we have to let y be 0. So let us solve for that. For the x-intercept, let y be 0. So let us solve. We have 0 equals 3x plus 1 over x plus 2. Remove the denominator, multiply it to 0. So we have 0 equals 3x plus 1. Solve for x, you will have negative 1 equals 3x. Divide both sides by 3. You will have negative 1/3. Therefore, our x-intercept is x equals negative 1/3. As for the OA, since there is horizontal asymptote, it follows there is no oblique asymptote. Next, for our y-intercept, let x be 0. So, making the 0 and this one 0, we only have the quotient 1 over 2. Therefore, our y-intercept is y equals 1/2. Next function, we have f of x is equal to x squared minus x minus 6 all over x squared minus 9. In this case, as you can see, the numerators and denominators are both factorable. So let us see if we can still simplify the function. So the factors of the numerator, we have for x squared, x and x. Factors of negative 6 that when added will result to negative 1. We have negative 3 and positive 2 over x squared minus 9. So this is difference of two squares. So we have x plus 3 and x minus 3. As we can see, numerator and denominator, we have a common factor. So we can remove x minus 3. Therefore, this function is equivalent to x plus 2 over x plus 3. So to find the properties, we are no longer looking at the original function, but instead the new function. Let's begin with the domain and the vertical asymptote. As we can see, we have the denominator x plus 3. Equate this to 0, we will have negative 3. So, vertical asymptote x is equal to negative 3. And for its domain, x is not equal to negative 3. Next, for the horizontal asymptote and for the range, as we can see, both numerator and denominator are linear functions. Their degrees are the same. Therefore, it's y equals 1. And since we have horizontal asymptote, it follows there is no oblique asymptote. And based in our HA, we have the range now, which is y not equal to 1. As for the x-intercept, let y be 0. So we have 0 equals x plus 2 over x plus 3. Multiply the denominator to 0. So we have 0 equals x plus 2. Solve for x, we have x equals negative 2. So negative 2 equals x is our x-intercept. For our y-intercept, we have y equals let x be 0. So 0 plus 2 over 0 plus 3. This gives us 2/3. So the y-intercept is y equals 2/3. For this item, f of x is equal to x squared plus 3 over x plus 4. Let us just find the asymptotes. First, the vertical asymptote. So once again, we have to equate the denominator to 0. So we have VA, x plus 4 equals 0. Solve for x, it is equivalent to negative 4. Next, for the HA, let us base it on the degrees of the numerator and denominator. The numerator has a degree of 2. The denominator has the degree of 1. Therefore, the numerator has a greater degree with the denominator. In this case, it means to say that the horizontal asymptote is none. Since HA is none, it follows that the OA exists. So the question now is how to find the OA. So to find the OA, we have to divide the numerator and the denominator. So here, let us do synthetic division, the lesson you have learned when you were in grade 10. So our divisor, x plus 4, equate it to 0. So we will have x equals negative 4. So using synthetic division, we have to place it here, -4, and the values to be placed here are the coefficients of the dividend. So the dividend is x squared plus 3, and it's not complete, so meaning the middle term is 0x. To make it complete, take out the coefficients. We have 1, 0, and 3. And in synthetic division, first bring down 1. 1 times -4, it's -4. Add, we'll have -4. Once again, the operations are multiplication and addition. Multiply, we have 16. Add, we have 19. So in this case, the oblique asymptote gives us the quotient. Take note that if there is a value at the end, it means to say that this is the remainder. If this is 0, meaning there is no remainder. In this case, all we need are these two values, and our oblique asymptote is given by y equals mx plus b. So the m refers to the first coefficient, so that is 1x, and then the b is the second number, which is -4. So this is our oblique asymptote. So again, to find the oblique asymptote, use the concept of synthetic division. So again, VA x equals -4, HA is not, OA is equal to y equals x minus 4. After giving you several examples, kindly try the following items. Find the intercepts, asymptotes, domain, and range of this function f of x is equal to x minus 2 over x plus 2. You may pause the video so you could try this item. Let's check your work. VA, we have x equals -2. Domain, x should not be equal to -2. HA is y equals 1. Therefore, there is no oblique asymptote. For the range, it's y not equal to 1. For the x-intercept, it's x equals 2. Y-intercept, y equals -1. Were you able to answer all of this? If yes, great job. Now, here is the summary on how to find the properties. For the domain, just simply equate the denominator to 0 or base your answer on your vertical asymptote. For the y-intercept, it is the value of y when x is 0. For the x-intercept, it is the value of x when y is 0, or equate the numerator to 0. For the vertical asymptote, just simply equate the denominator to 0. For the horizontal asymptote, take note of these three cases. If we have n is less than m, referring to the degrees of the numerator and denominator, horizontal asymptote is y equals 0. When the degrees are the same, y equals a over b, referring to the quotient of the leading coefficient of the numerator and denominators. When n is greater than m, take note that there is no horizontal asymptote, but instead there is an oblique asymptote. And to find the oblique asymptote, you have to divide the numerator and the denominator, and whatever is the quotient, that is your oblique asymptote. And for the range, you have to sketch the graph of the function or base it on the horizontal asymptote. So that's the end of our discussion on rational functions. I hope you were able to understand how to find the properties of rational functions. So once again, thanks for watching. So for those who are new to my channel, again, don't forget to subscribe to my channel, Math Room by Teacher Joanne, and click on the notification bell to be updated. Bye everyone! See you in my next video.